So we've got our review sheet problems, and hopefully these look pretty familiar to you all. Make sure I can, so you guys can see it. All right. So we are going to take a look at these problems and see what we can figure out. So first says, consider the following position versus time graph. We're given a graph here where we have a line with a constant positive slope. It says, determine the average velocity of the object. So if you remember, to figure out our average velocity, we're going to need to look at our change in position divided by our change in time. Another way to think about that is final position minus initial position divided by final time minus initial time. So I'm going to pick 2 points on here. And I'm going to pick 0. I'll go all the way up here. So the first thing I need to do is look at how my position changed. My object moved from 10 to 60. So I'm going to do 60 meters minus 10 meters to find my change in position. And to find my change in time, I'm going to start with my final time, which was 6 seconds, and subtract from that 0 seconds. So I find that I have 50 meters over 6 seconds, which is going to be less than 10. It's probably 8 something, right? 60 divided by, 50 divided by 6. So I got 8.3 meters per second. My guess is that the most common mistake on this problem is that students will look at this point, 60 meters in 6 seconds, and just divide the 60 by 6. And you would get the wrong answer because this doesn't go through the 0, 0 point. It goes through 0, 10. So because it has an intercept, you have to be careful about the way that you calculate this. Next, it says, write a mathematical expression to describe the motion of the object. So we're looking at something that's a straight line. That's going to be y equals slope times the x variable plus the intercept. But we don't just want to report that. We want to fill in as much information as we can so a person could look at that and really understand what we're doing. So I'm going to replace my y with position. And I'm just going to get that from looking over here at the graph. The thing that's on the y-axis is my position in meters. And we want to make sure we include units too. It's equal to the slope, m, is going to be our average velocity for this line that describes motion. So we're going to take that from what we calculated above and say 8.3, and that's going to be in meters per second, times our variable from the x-axis, which is time, seconds. And then lastly, our intercept. And don't forget that the intercept has units too. The place where this line is crossing the y-axis is at 10 meters. So we write 10 meters. Doesn't have to have the parentheses on it, but we need all of that information to be able to recreate this graph. So when you write your equation, a good thing to do is think about, okay, what if I had just the information that I was reporting for my mathematical expression, would I be able to complete the graph? And so that's why having all those units matters, because we need to know the units that go on our axes. Anybody have any questions about number 1? All right. Next, we're given a velocity versus time graph for an object. Excuse me. So first, we're asked to describe the motion of the object. So I can see that I start with a positive velocity of 4 meters per second for 2 seconds. Then I have a negative velocity for 1 second. And then my object has a velocity of 0. So it stops moving. I can also figure out how far my object traveled if I look at this, the area here. If I'm moving at 4 meters per second for 2 seconds, that means I'm going to travel 8 meters. So this represents 8 meters of motion, where I have each block here represents 1 meter. 1 meter, 1 meter, 1 meter, 1 meter. If we know that each block represents 1 meter, we can figure out how far our object traveled in this 1 second. This is going to be minus 1 meter because it's the opposite direction, right? So another way I could calculate this is by looking at my velocity, my minus 3 meters per second times 1 second, and end up with 3 meters because my units will cancel there too. Here my object isn't traveling at all. object not moving. Okay, so when I describe my motion of my object, I'm going to say from 0 to 2 seconds, my object is traveling I could just say it's traveling at plus 4 meters per second. Another way that I could say that is my object is traveling in the positive direction at 4 meters per second. It's important to have both the sign and the magnitude there. From 2 to 3 seconds, my object travels at minus 3 meters per second. Or it turns around and travels the opposite direction at 3 meters per second. And then I can say that my object stops at 3 meters. Sorry, at 3 seconds. Anybody have any question about describing the motion of the object? If you do, you can feel free to unmute yourself or put something in the chat. Okay, next it says draw a corresponding position versus time graph. Number the axes. You may assume that the object starts from 0 position. So that's nice. So we know that it's going to start at 0. So I can put a dot there. We know that after 1 second, if we look at our graph up here, after 1 second, our object has traveled 1, 2, 3, 4 meters. After 2 seconds, it's going to travel 8. So I need my scale to go up to at least 8. So if I start at 0, 1, 2, 3, 4, 5, 6, 7, 8. So I'm just going to make mine so that each one of these grid marks represents 1 meter. So after 1 second, I've traveled 4 meters. So I'm going to make that 1 second, 4 meters. So there's my point. After 2 seconds, I've traveled another 4 meters for a total of 8 meters. So 2 seconds, I have 8 meters. So there's the first part of my motion. It's a pretty steep positive line. And we would expect it to be positive because our velocity is positive. Then we said our object turns around and travels 3 meters in the opposite direction for 1 second. So I'm going to go down 3 for my next one. 1, 2, 3. And if we added these together, we could add these together and say that there's 4 plus 4 is 8 minus 3 is 5, and that's in fact where we are after 3 seconds. Then my object stops moving. So for my position versus time graph, that means my position is unchanged. There's no change in the location. So I'm going to draw a straight line that goes across. So there we have it, position versus time graph. I'm asked how far did the object travel in the interval 1 second to 2 seconds? And we solved this a bunch of different ways on here already. So if you've solved it in other ways, you can write on your notes that you figured it out someplace else. Another way that we could do it is we could say that the change in position is equal to our average velocity times time. So we know that in that time, our average velocity was 4 meters per second. And the time difference there is 1 second. So I'm going to do something to show my work there. I can also show it by drawing like a little arrow here. We can do it by looking at the graph there. You could also do it by looking at the values over here. So you could even say that your change in position is equal to your final position minus your initial position, which is the same as your position at 2 seconds. Minus your position at 1 second. So at 2 seconds, we're at 8 meters. At 1 second, we're at 4 meters. And we get 4 meters. So there's lots of different ways that you could solve that and be right. Anybody have any questions about part C? Rachel, I appreciate your head nodding. You're the only person who's giving me feedback right now, and I value that. Okay, so the last one is find the displacement from 0 seconds to 5 seconds and explain how you got your answer. So for displacement, we need to know only the difference between the initial position and the final position. So that's all we need to know. Displacement is difference. So difference, if my kids are in elementary school, so when they see difference, they think subtraction. It's the difference between final and initial position. Okay, so our final position, our position at 5 seconds minus our position at 0 seconds. At 5 seconds, our object is at 5 meters. At when time is 0, we're at 0 meters. That's kind of an interesting coincidence, right? These numbers that I used as subscripts here are referring to the time and not to the distance. So it's interesting. And our object has traveled 5 meters of displacement in the positive direction. So if I was only interested in the start and the finish, I would just be looking at the relationship between those 2 points. Anybody have any questions about number 2? Okay. So on the back, it says find the average velocity from 0 seconds to 5 seconds and explain how you got your answer. So velocity, remember, is only concerned about the initial position and the final position. So that's going back to this green line that we had on the second page. So if those are the only things that I care about, I'm going to figure that my average velocity is the position at 5 seconds minus the position at 0 seconds, which we already decided was 5 meters. And then the time at 5 seconds minus the time at 0 seconds, which is going to be 5 seconds, right? So that's it's going to be 5 minus 0 seconds. So if we've got 5 meters divided by 5 seconds, we're looking at 1 meter per second. So this line here gives us a velocity of 1 meter per second. When we calculated earlier that our velocity here, we're told our velocity is 4 meters per second, and our velocity in the second part is minus 3 meters per second. The average of those two is 1 meter per second. Then it says find the average speed from 0 to 5 seconds. Explain how you got your answer. Remember, speed is going to be different than velocity because now we care about the total distance traveled. And we're going to add those together basically by adding together the absolute value of all those distances. So our distance from 0 to 2 was 8 meters. The distance traveled from 2 to 3 seconds was another 3 meters. So we're going to add those two things together. 8 plus 3 gives us 11. So our total distance traveled here is going to be 11 meters, while our time is still 5 seconds. So this is going to be a little bit of a different value. If we're looking at those things, we're going to find our object was moving faster than was implied by our average velocity. So 11 divided by 5 is going to give us 2.2 meters per second. It's quite a bit faster. So I'm just going to write here on my notes, distance is the sum of absolute value of all displacement. It's just another way to think about it. All right, next. Excuse me. A bird travels toward 0 position, then suddenly reverses direction. Right? We expect this from birds. It says find the average velocity from t equals 0 seconds to t equals 5 or 10 seconds. So that's just this first piece. So if we want to know average velocity, we're looking at our change in position divided by our change in time. Our position ends up at 10 meters and started at 30. So I'm going to do my final position minus my initial position divided by my final time minus my initial time. And I end up with minus 20 meters because I'm moving in the negative direction for 20 meters divided by 10 seconds. So my average velocity is minus 2 meters per second. So that tells us that this piece of the graph, we have a velocity of minus 2 meters per second. Next, find the average velocity from 10 to 20 seconds. So from 10 to 20, we're going to do the same thing. Our average velocity is equal to our change in position divided by our change in time. The change in position, let's see, our final position is going to be 25 meters. Our initial position is 10 meters. Oh, sorry. I forgot to bring my corrective tape with me today, and it's throwing me off. Yeah, I don't have extra one. All right, 25 meters minus 10 meters. For my time, I end up at 20 seconds. And my initial time was 10 seconds. So overall, I have 15 meters traveled in 10 seconds. So overall, my average velocity is positive 1.5 meters per second. This makes sense to me because if I look at this, I've got a positive slope and it's not quite as steep as my first piece of the motion. So that makes sense to me. Do you guys have any questions about finding average velocity there? No. All right, next we're going to talk about average speed. Remember, speed is our total distance divided by time. So we're going to look at absolute values of things. So speed, our total distance from 0 seconds to 20 seconds, we're looking at everything to this point right there. So our object travels, let's see, distance over time. Our object travels in this first part 20 meters. We calculated that before, but what we care about here is the total distance and not the sign that goes with the distance. So I'm going to record that as 20 meters plus the distance traveled from 10 seconds to 20 seconds, which is going to be another 10 meters. And the total amount of time there is 20 seconds because we're doing 20 seconds minus 0 seconds. So 30 meters over 20 seconds is going to give us, I believe that's 0.67, but I like to double check. 30 divided by 20. Oh, sorry, 1.5. That's why I double check. So I was traveling, my object is traveling at 1.5 meters per second through that time. It says determine the average velocity from 0 to 20 seconds. So what I'm going to do there is just look at what's happening from this point to this point, which means I'm going to expect a negative velocity because my object overall traveled in the negative direction. Another way to think about it, it traveled more in the negative direction than it did in the positive direction in that time. So our average velocity is going to be our change in position divided by our change in time. Our final position is 20 meters. Our initial position is 30 meters. I was getting ahead of myself. Divided by 20 seconds of travel time. So this is going to give us minus 10 meters in 20 seconds or minus 0.5 meters per second. Lastly, to find the velocity at 5 seconds, what we're going to do is look at what the velocity is doing at that point. Now, we know that this velocity is constant all the way along this line. So we can pick any points in here to figure out what the velocity is. We could pick 0 to 5, we could pick 5 to 10, we could pick 0 through 10, or we could say, hey, we already calculated the velocity for every point along that line, right? It's this minus 2 meters per second. So we could say, we calculated that. So I'm going to say we calculated that in 3A. We already did that. It's up here. But what's important to recognize there is that the velocity of this point in the middle is going to be the same as the velocity of any point from 0 to 10 seconds. You guys have any questions about number 3? Hopefully this feels very doable to you guys. All right, last page. A basketball initially travels at 3 meters per second for 3 seconds. Describe the motion of the ball after 3 seconds. So we're given this graph, 1, 2, 3. We're looking at the object after 3 seconds. We're told on this graph it's traveling 3 meters per second. So there's our 3 meters per second. That means that after 3 seconds, according to our graph, we have a ball that's traveling at minus 1 meter per second. So I'm going to say the ball travels at minus 1 meter per second from 3 to 5, 6, 7 seconds. So it turned around, right? It changed direction. We're not really told what direction it was going to begin with, so it's kind of hard to figure out what happened there, but it could be somebody stole the ball. It could be somebody threw it up in the air 3 meters and it turned around and came back down. We don't know what direction it was, but we do know that it changed direction. And that it moved slowly, and it came at a constant speed. So if it was a constant velocity, it probably means it wasn't coming straight down, but you guys don't know that yet. All right, next, draw a quantitative motion map that represents the motion of the object. I start moving in a positive direction at 3 meters per second. To make my life easier, because my page isn't that long, I'm going to make each one of these 3 meters. So I got 3 meters, 6 meters, 9 meters, because I travel 9 meters away from 0 here. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So that means each second I'm going to have a dot at each one of those bars. That's where I end up. And then I turn around. So I'm going to move that down there. So here's t equals 0, t equals 1, t equals 2, t equals 3. After 3 seconds, I change direction and I'm moving at 1 meter per second on the return, right? But I only do this for 1, 2, 3, 4 seconds. So I got to divide this up now into thirds. So I'm going to do the best that I can here. So 3, 4, 5, 6, 7. My object turns around, my basketball turns around and comes back the other way. How far did the ball travel from 3 to 7 seconds? There's a couple ways you could do this. You could find the total distance by looking at your average velocity times the amount of time. Our average velocity there, again, given by the graph, is minus 1 meters per second times 4 seconds. So minus 4 meters. Or I can look at the graph and I can say, well, the area between the line and this line and my 0 line is going to give me that distance. So I could say each block is minus 1 meters. There are 4 blocks. So 4 meters in the negative direction. You guys have any questions about number 4? Okay. Lastly, a race car reaches a speed of 95 meters per second. So I'm going to record that speed of 95 meters per second. After it's 450 meters past the starting line, if the car travels at a constant speed of 95 meters per second for time for 12.5 seconds, how far will the car be from the starting line? So hopefully you recognize some of these things. The speed here is going to be our slope. Past line, this is our intercept. And time is time, right? So we could use this information to make a graph if we wanted to, where this is 450 meters, our slope is 95 meters per second, and the total amount of time that's traveled is 12.5. We could write this as an equation. Our position in meters is equal to 95 meters per second times time in seconds plus 450 meters, because that's where we started. So we can use the speed times the time to figure out how much the position changed, and we're going to add it to where they started. So we're given that 12 seconds. I'm going to do 95 meters per second times 12.5 seconds plus 450 meters. Grab a calculator. 95 times 12.5 gives me 1,187.5 meters. Don't be afraid to hang on to all your numbers until you're done with your math. I'm going to add 450 to that. So we get a total of 1,637.5 meters. So that's how far the car is from the starting line by the time we get to the end of that 12 seconds. Okay. Do you guys have any questions about that problem? This is probably the toughest one that you guys will have because we haven't had tons of practice on these. But what I'm hoping is that when you see a problem like this, you can identify the way that it would fit into an equation. And again, another way to think about this is position is equal to average velocity times time plus initial position. So if you get really stuck, that's the equation that you're going to use. And this is the same as the one that you guys figured out at the very beginning when we did that buggy lab. Okay, so where we're headed is I'm going to give you guys an assessment tomorrow. It's going to be something that's open note. To some degree, you could use the internet for it, but I'm not sure if that's going to be the most efficient use of your time. Sorry, I just got a text message. So I don't know if it's going to be the most efficient use of your time to try to Google things. So what you're going to want to do is take a look at your packet, some different kinds of, I'm not going to give you a new type of question. So things will look similar, but you may want to jot down or highlight things like relationships between things like the slope of a position versus time graph gives you a velocity. Or this relationship here where our position is equal to average velocity times time plus initial position. And then I think you'll be in good shape. Do you guys have any questions for me before I let you go? All right, guys, I hope that you all have a wonderful day. I'm sorry for keeping you over 1 minute, but I hope that that information was helpful to you. Let me know if you have any questions before tomorrow, and I'll see you then.